And also thanks for actually setting up this series of seminars. I think it's really great for the community these days when we can't really travel. So the title of my talk is Identification and Learning of Stable Dynamical Systems, Linear Neural Network and Polynomial Models. And this is joint work over quite a few years now with several co-authors, roughly in chronological order here. And actually, a subset of these co-authors and I are in the process of writing a kind of a tutorial paper article about this material. So this is a bit of a test run for that. So if I would really strongly value any feedback either during the talk or after the talk about the parts that were clear or unclear or that kind of thing. Okay, so let's get started. So what's the objective of this talk? Basically to give an introduction to imposing stability and stability-like constraints when identifying or learning state space dynamical systems. An outline of the talk, I'll start with the problem and motivation. Then through a fairly simple example, I'll walk through the main idea that underpins our approach, which draws together kind of a few ideas from robust and nonlinear control, but might be a slightly unfamiliar combination of them to some. Then I'll go through a few particular cases of models that you might want to impose stability on while you're doing system identification. So starting with kind of the gentlest case of linear time invariant models, then moving on to recurrent neural networks and polynomial models. And with each of these, as we go from linear to RNN to polynomial, each step allows us to introduce some kind of new concepts along the way. Then we'll see how we go with time. There's a bunch of kind of variations and extensions of these ideas that we can discuss, but we may run out of time. Okay, so problem and motivation. What are we doing and why are we doing it? So basically, if you're not at all familiar with system identification or learning of dynamical systems, we can think of it in terms of some other standard problems related to dynamical systems. So the most basic one would be simulation, which is when you know a model and you know an input to that model and you want to figure out what the output from that model is. A kind of an inverse problem to that would be a version of a planning or a control problem where you know a model and you know some desired output, and then you want to figure out the input that would produce this desired output, either exactly or approximately according to some cost function. And a third, also kind of an inverse problem, is when you know both the input and the output of a system, but you don't know the model. And so the objective is to come up with the model. And this goes under various names in different communities. There are lots of, you'll often find similar methods and ideas under different names. So in control, we often call it system identification. In machine learning, it's called learning of dynamical systems, which is essentially mathematically the same problem, but typically different example problems are of interest and different model structures are more common. Also things like parameter estimation, model calibration, time series modeling, reduced order modeling have similar mathematical problem statements. So this is the general problem we're looking at. Given inputs and outputs of a system, come up with a model. And so we can think of an identification or a learning algorithm as a mapping from data sets to models. So Z here is some data set, and we produce some model M, which is taken from some model set, calligraphic M. And actually most of my talk is going to be about constructing this model set M. So these are the kind of data sets, and the model sets are the two basic ingredients. Usually in system identification, we can think of the data set as consisting of finite length input and output sequences. Here, the inputs and the outputs may be vectors, or they may be scalars, but typically they're of finite length. So we take this pair of U and Y as our inputs and outputs, as our data. Then the model set, calligraphic M, this should be some set of possible or plausible models. And this can be made precise in many different ways, or it may be difficult to make precise. And roughly speaking, a model should be something that maps new inputs to simulated or predicted outputs. But there are many different things which one might call a model. Could be deterministic, could be stochastic, it could be set valued, could be a behavioral model. There are many different types of models, dynamic models one might have. In this talk, I'm going to keep things as simple as possible, and we're just going to look at deterministic models. Okay, so with those ingredients, the dominant approach to system identification is to formulate an optimization problem. This is not the only approach. There are other approaches such as Bayesian methods and set valued identification methods that don't exactly follow this structure, but I think it would be fair to say it's the dominant approach. So the idea is you try to estimate a single model, you could call this a point estimate of a model, as the minimizing model in the model set of some cost function. And the cost function depends both on the data and the particular model. So in order to apply this approach, you need to add 2 extra ingredients, as well as we've got the data set, we've got the model set. We need to define the cost function. So the cost function should somehow measure how well does the model do at matching the data set. There are several possible choices here. Perhaps the most basic and probably most widely used is just the least squares error in the simulated output. So here, y tilde represents the data set, so the recorded data of the outputs, and y without the tilde represents the simulations from our model. And you just square the differences and add them up. There are lots of variations on this. Instead of open loop simulations, you might look at one-step or multi-step predictions. When you're looking at stochastic models, this kind of least squares criterion can often be related to a maximum likelihood criterion and also maximum a posteriori probability. And so there's variations on those. In addition to defining a cost function, you need to figure out some way of actually solving this optimization problem. And that is usually far from trivial, because what we're dealing with here, whenever we include these model simulations, for most kinds of things you would want to minimize, you actually end up with quite complex non-convex optimization problems here. But all the standard optimization approaches are thrown at this, like gradient descent, Newton's method, and so on. Also some kind of more specialized techniques such as the EM, expectation maximization algorithm. And we've worked in the past on developing kind of convex bounds for these sorts of problems. Actually, in this talk, I'm going to basically leave this here. I'm not really going to talk about the cost functions or the methods of fitting the model. From now on, this is just kind of setting the scene. From now on, I'm essentially going to be talking about constructing the model set M so that it satisfies some stability properties. Okay, so what kind of models are we dealing with? As I mentioned, models can be essentially almost anything you can imagine, but probably the most familiar class of models, at least to a control audience, would be state space models. So these may be linear or nonlinear. We can write them in this general form where you might have some function f defining the mapping from one state to the next, also depending on the input, and a mapping g defining the output given a current state and current input. And then there's a parameter vector theta, which is used to parameterize these models. So this might be elements of matrices or coefficients in a polynomial and so on. Now, when you have such a parameterization, then when we refer to a model set, we're talking about now theta should live in some capital theta, which is a subset of a real vector space. So basically what we're now trying to do is come up with some subset of parameters that define well-behaved models here. And having chosen this kind of state space model structure, of course, if we're searching in part over the functions f, anytime we have xt plus 1 as a function of xt, we've got feedback happening, we've got memory in the system, so there's a risk that we will introduce instability in the model. So why might we want to enforce stability? Well, it might just be a requirement of whatever you're using system identification for. It's actually not uncommon. It's not hard to get a standard method of system identification to produce an unstable model, even when the system is stable. Often even when the system you're measuring from is very stable, you can get standard system identification methods to spit out an unstable model. And this is often going to be unacceptable for the purpose you're using the model for. Even if that doesn't happen, so the standard method might give you a stable model in some sense, the solutions might remain bounded, they could still be erratic. So they might be kind of more sensitive, if not completely unstable. And stability constraints we've often observed can be a very effective regularizer. So stable models are in a sense smoother than, more stable models are in a sense smoother than less stable models. And although it won't be the topic so much of this talk, being able to learn or optimize over sets of stable models is actually very useful in a lot of other problems. For example, we can formulate nonlinear observer design problems in terms of searching over stable nonlinear systems with some additional constraints. There are many controller optimization problems based on versions of the Euler parameterization where you need to search over some stable parameter, which is basically a stable system. And as we might see if we get time, we can even apply this kind of thing to traditional machine learning problems such as image classification, in which stability and robustness turn out to be useful concepts. Okay, so that's on why to enforce stability. But why do we even learn the feedback model? We could perhaps solve this problem by just fixing the feedback dynamics, the function f here, to be some a priori known f, which is known to be stable, and then only searching over the output model. And this is actually a very common strategy. So for linear systems, finite impulse response models can be thought of in this way, where this the dynamics here is essentially just recording a fixed history. Also model structures such as stable spline models and various models where you effectively fix the poles in a model and search for the zeros, or fix the denominator in a transfer function and search for the numerator. And this is using various sorts of expansions of stable models such as Laguerre, Ritz, Kautz expansions, and so on. And this is quite common in system identification. In the nonlinear case, when we can extend this idea to nonlinear finite impulse response models, Volterra series, convolutional neural networks, and so on. Basically, you have some known stable dynamics, and then you search for the output mapping. So the reason why you might not want to do this, and you might want to search for the dynamics itself, is that these model classes are often very inefficient. You might need many, many parameters, very large models to identify systems with resonance, essentially systems that have long-term memory about inputs that appeared far into the past. A second reason is that a state space model can often be a very useful structure in and of itself. So the concept of a state and the concepts that go with that of stability and so on, these are model structures that are very useful in system analysis, control design, motion planning, and so on. Okay, so given all that, why would we try to construct convex sets? So we will be looking at constructing convex sets of stable models. In fact, you could argue that since usually in system identification and machine learning, we're trying to minimize some highly non-convex cost function anyway, what's the point of trying so hard to get a convex model set? The motivation here is really that there's a kind of a difference between the way we treat the cost function and the model set. We might want to find a good model, so try to find a model with low fitting error. But on the other hand, we might have a hard requirement that it is stable. So this is kind of a hard versus a soft requirement. And usually model constraints are imposed during the fitting process via some kind of projections or barrier terms. And these are generally much simpler and much more computationally efficient if the model set you're working with is convex. Okay, so, and just before we move on to the real material, I'll just mention that most of the numerical examples I'm going to show in this paper are based on some variation of a simple mass spring damper setup like this, sometimes with a nonlinear spring. So it's not really crazy models that we're looking at here. It's kind of fairly common model structures, but even with this kind of system you're trying to identify, you do very often get unstable models. Okay, so that's the kind of the problem setup and the motivation. For the next few minutes, I'm going to try to introduce the main overarching idea in fairly general terms. And then following that, we'll see some explicit realizations of that for the three model classes I mentioned before: linear, neural network, and polynomial models. So to introduce the main idea, let's consider for the moment a fairly simple problem of establishing that a system x of t plus 1 equals f of xt has the origin as a globally stable equilibrium. And in fact, for this particular example, x is a scalar. We can let x be a scalar. Later on, it will be higher dimensional. So what does this mean? It means we want to establish that f of 0 equals 0, and furthermore that x of t converges to 0 as t converges to infinity from all possible initial conditions of this dynamical system. Okay, so what do we do? The first thing we do is think maybe we can construct a Lyapunov function. And there's quite a few subtle variations on Lyapunov functions, strict and non-strict versions, so on. The particular structure I'm going to use, and which is useful for what follows, is like this. We actually just need V to be non-negative, not necessarily strictly positive definite in any sense, just non-negative. So it's at V of x is greater than or equal to 0 for any x. And then we want to find a V that satisfies the following inequality. So basically V of the next state, f of x, is less than or equal to V of the current state minus some possibly small positive, some possibly small positive number epsilon times the absolute value of the current state. So basically, this is just saying that V of x shrinks a little bit over time as the system evolves. Then if we sum this relationship over some finite time sequence, basically we get here on the left-hand side, V of xt plus V of x 1, 2, 3, and so on up to t. And on this side, V of x 0, 1, 2, and so on up to t minus 1. And so most of those cancel. All that we're left with is the last x of t on the left-hand side and the first x of 0 on the right-hand side. And then we subtract the summation of all of these epsilon x squareds. And since we have enforced that V is non-negative, we know that this part here is greater than or equal to 0. And also, since capital T was arbitrary, we can this also holds as we take t going to infinity. And then we can rearrange things a little bit, and we just get this. Basically, that the state xt is in L2, meaning it's square summable. And in particular, No matter what our initial condition is, we take v of x naught divided by epsilon, and that's an upper bound for the sum of x of t squareds. And if you're not familiar with L2 stability, if you just realize for this summation to converge to a finite number, so this number is fixed depending on the initial condition, for this to converge, it must be the case, since all of these are non-negative, it must be the case that these converge to zero. And in fact, these must converge to zero quite rapidly. This kind of stability can be related also to exponential stability. Okay, but the problem here when we're talking about identification or learning dynamical systems is that what we want to estimate is both the function f and its certificate of stability. So the common scenario for using this kind of Lyapunov argument is that the model f is known, and we just want to find some Lyapunov function v that verifies this. And there's various computational tools that have been developed to try to do that. And in fact, if f is known, then this inequality here is actually a linear inequality in terms of the function v. It's a convex constraint on the function v. But if we're trying to learn both v and f simultaneously, this is actually a complicated function, because basically f, however we're parameterizing f, that then gets passed through some nonlinear function v, and it will generally make the set of possible f's very complex. So another way we can establish essentially the same thing is to introduce some multipliers. And this is for those who are familiar with the S procedure in robust control, or positive Stellensatz in semi-algebraic geometry. This will look familiar. Basically, the idea is you take our stability condition here, but instead of putting f of x inside the brackets here, we just have some other variable, x plus. But then we add with a Lagrange multiplier here, lambda, the term x plus minus f of x. And if this inequality holds for all pairs x and x plus, then we can establish stability, essentially because the blue part here vanishes for any solution of our model. And since that blue part vanishes, we're just left with this part here, which was the stability condition. Okay, so that helps perhaps. We've now disentangled v from f, but we're still stuck with this Lagrange multiplier. So if you're familiar with this kind of technique, you probably know that for this to really be effective, you have to somehow be able to search over the multiplier lambda. Otherwise, you end up with extremely conservative conditions. So how can we search for this? We've got products here now between lambda and f, so that's going to cause problems. Also, this is somewhat limiting in terms of what we know. So if we know that x plus minus f of x is equal to 0, we also typically know that x plus minus f of x squared is equal to 0, and all other powers of it, and lots of other nonlinear functions of it, and so on. So somehow we're not using all the information we have about our model here. So the idea, really the main idea in a lot of what we do, is to consider instead implicit models, and we'll call that m of x and x plus, and this is defining an implicit relationship between x and x plus via some function of both which equals 0, instead of an explicit model which defines x plus in terms of f. And then we replace this term with m here. So it's the same thing. The difference is that these representations can be highly redundant. So if you write in this explicit form, there's only really one f that represents this model. But in this form, you can have many, many different m's that represent the same model. And that kind of allows us to absorb some of the flexibility that we need from the multiplier into the model itself. For example, if we have some explicit model f, we could write the natural implicit model x plus minus f of x here. But also, if we have any invertible function h, we can write h of x plus minus f of x, or h of x plus minus h of f of x. And as long as h is invertible, all of these different m's represent the same model. So now we've got many, many different implicit models here that correspond to the same explicit model. And that gives us, in some sense, and we can make this precise, it gives us in some sense the flexibility that we need, even if we fix lambda. So that's kind of the main idea of this approach. As a side comment, when we're using implicit models, we typically need to do a little bit of extra work to ensure that it actually does correspond to a well-posed model, i.e. for any x, there exists a unique x plus, basically that this is solvable for x plus. We'll see a few examples of how we can do that later. So maybe I'll pause at this point. If anybody wants to ask a question about that kind of the main idea of the approach, this would be a good moment. Otherwise, I'll kick on to linear systems. Okay, so LTI models, this is kind of, yeah, I guess a gentle start where we can introduce or show how the method works. So the problem here is we want to identify a linear state space model parameterized by matrices A, B, C, and D. When we're talking about stability, A is only the really the only thing that matters. B, C, and D don't affect stability in any way. And stability of this system depends on, in particular, the spectral radius of A. So the magnitude of the largest eigenvalue should be less than 1. So you may or may not be familiar with the fact that this is actually a non-convex constraint. So we can easily construct two matrices here, AA and AB. Both of these have spectral radius of 1/2, so both of them are stable. But if we take their average, which is a convex combination of the two, we get this matrix, and this matrix has a spectral radius of 1.25. So this is unstable. So you can basically have two stable systems, draw a line between them, and you'll get unstable systems somewhere on that line. It can happen, doesn't necessarily happen. So this is a non-convex constraint, just trying to constrain the spectral radius in terms of the parameters of A. Okay, so what can we do? First of all, before we get to the stability constraints, I'll just mention that, of course, for linear systems, essentially all forms of stability are equivalent. They basically all boil down to this spectral radius condition on A. That's not true for nonlinear systems. You can have many distinct forms, concepts of stability that are not equivalent. But partly to help kind of smooth the road towards the nonlinear case, but also partly just to simplify notation, even for the linear case, I'm going to look at incremental stability. So what do we mean by incremental stability? We mean stability of pairs of solutions. So here delta is for some two possible solutions of this model, XA and XB, delta is just XA minus XB. So you can see, for example, this is a simple linear system forced by a sinusoidal input with some offset. And there are two different initial conditions here, which converge towards the same steady state solution. So this is kind of the familiar unforced or homogeneous solution that you might have learned about in basic linear systems courses. It's convenient when talking about stability in the context of system identification because it takes the input out of the picture. We're just looking now at the A matrix, and we can basically ignore everything to do with U because it affects both realizations of the system, both solutions of the system similar in the same way. And also, as I mentioned, it's a useful setup for thinking about the kinds of nonlinear stability that we'll work with later on. Okay, so we've got this incremental system, delta plus here, this just means delta t plus 1, and this just means delta t. So delta plus equals A of delta. Okay, so how are we going to apply this main idea that I introduced before? So first of all, we need to think about the Lyapunov functions that we're going to search for. The nice thing about linear systems, of course, is that if they are stable, if and only if this stability can be established with a quadratic Lyapunov function. So without loss of generality, we can choose V of delta to be delta transpose P delta, where P is a positive definite matrix. And then the condition that we want to establish is that delta plus P delta plus minus delta transpose P delta is less than or equal to minus some small constant multiplied by the norm of delta. So basically this is kind of the Lyapunov decrease condition. Okay, so the main idea that we just introduced is that we want to combine this Lyapunov decrease condition with the model equations, but we're going to get the flexibility we need in terms of the multipliers if we swap from an explicit model, like we had here and here, to an implicit model. So the implicit model we're going to use for linear systems is like this. This might look like, if you're familiar with descriptor systems, this might look familiar. However, we will in fact enforce that E is invertible. So there are no algebraic equations here. This is really just an equivalent representation of the explicit form, but it's a useful parameterization. So we've got now E, F, and K. And in terms of the incremental dynamics, we can write this as E of delta plus equals F of delta. So now we do our kind of main trick, which is we take the Lyapunov decrease condition here, and we add to that some term which has some multiplier here times the implicit model in terms of the increment. So we've got E delta plus minus F of delta. And then this should be less than or equal to the amount we want the Lyapunov function to decrease by each time step. And so again, the basic idea is that because our model is defined by this equation and this incremental equation, for any solutions of our model, E delta plus minus F of delta will be 0. So this term vanishes. And that means that we have this term remaining, which is the Lyapunov decrease condition. So basically, what we have now here is just a inequality on a quadratic function in terms of two arbitrary variables, delta and delta plus. But if these arbitrary variables, delta and delta plus, happen to correspond to solutions of the model, then the Lyapunov decrease condition will hold. And actually, we can kind of collect the various terms for delta and delta plus and write this as a matrix inequality, a linear matrix inequality, in terms of the Lyapunov parameter, the Lyapunov matrix P, and the model parameters F and E. And this is what we get. And this, it can be fairly easily shown that this is a necessary and sufficient condition for a linear system to be stable. So furthermore, if we look at the bottom right corner, we see that P is positive definite. And then since P is positive definite, this means the top left corner means that E plus E transpose is positive definite. And this further implies that E is invertible. So we can get back our explicit model just by setting A equals E inverse F. Okay, so this LMI here, linear matrix inequality, actually encapsulates both our stability constraint and our well-posedness constraint, that E is invertible, in one inequality. Okay, so that's pretty much it for linear systems. We've seen how we can apply the technique by choosing a structure for a Lyapunov function, choosing a structure for our implicit family of models, combining the two using some multipliers. And actually, I won't go through it here, but it can be shown that this implicit model structure really is necessary to get to be able to do the necessary and sufficient condition. If you tried, you could try to do the same thing here with the explicit model, delta plus minus A delta, but then there would be some stable linear systems you don't capture with this constraint, whereas by introducing the implicit model structure, you capture all possible stable linear systems. And then just as an example, I'll show how we've used this in identification of a linear system. We've applied the expectation maximization algorithm, which kind of iterates between fixing a model and estimating states. and then fixing states and estimating the model. And as we iterate back and forth between those, we can see the blue line here shows how the spectral radius evolved for the standard EM algorithm without any stability constraints, and it kind of rapidly goes up above 1. So you quickly find unstable models, and it actually never finds a stable model again. Whereas with our condition here, don't worry about that acronym, with our condition here, it stays below 1 and actually converges to the spectral radius of the true system that was used to generate the data. Okay, so that was linear systems. Actually, a fairly small jump from linear systems is recurrent neural networks. So that's what I'll jump to next. Basically, if you're not familiar with recurrent neural networks, they're a very flexible and popular class of nonlinear models, kind of seen a resurgence in popularity recently, although they've been around for a long time. So what are they? Basically, they're models which are combinations of some linear mappings, linear operators, which are estimated or learned. So these are the parameters. And then some usually quite simple scalar nonlinearities, and these are fixed. You don't identify the nonlinearities, they're just fixed in advance. And so the following form is common. You have x plus, the next x is some matrix times, this sigma is some nonlinearity, which is typically a scalar nonlinearity applied element-wise. And then there's some linear mapping of the previous state and the input and some bias term. And it can be shown that for most activation functions, this class of models over bounded domains represents a universal approximator of nonlinear mappings. As long as you let this W matrix get very tall and this W matrix get very wide and the number of activation functions get very big, then you can approximate arbitrary functions. And most common activation functions are actually slope restricted with some interval of possible slopes. Most of them actually with slope 1. There's some that are a bit different, but here's a couple of examples that are commonly used. One is the tan H function, hyperbolic tangent, and another one called the rectified linear unit is just the maximum of x or 0. So it's just flat for negative numbers and equal to x for positive numbers. So both of these have slope less than or equal to 1. And this is going to be the key property of them that we will use. In fact, we work with a generalized structure of recurrent neural networks, strongly motivated by the kinds of model structures that have been studied in robust control. So here we have this feedback interconnection of a linear time invariant discrete time model and a nonlinear component representing the activation functions. So here G is an LTI model parameterized by all of these matrices. In fact, we will use implicit versions of these. And then sigma here is some scalar slope restricted nonlinearity, which is applied element wise to the vector V to produce the vector W, which is kind of the disturbance input to G. Now this model structure, I called it kind of generalized. It actually includes a lot of commonly used model structures as special cases. So it kind of obviously includes all stable linear systems. We can just have all the terms that take in W set to 0, and we just get the linear part. We can also just set A equal to 0, and we get the kind of standard recurrent neural network structure. So we can kind of blend between, if we want, linear time invariant models and recurrent neural networks. And in fact, with the stability constraints that I'll show in a moment, we can cover all previously known sets of stable recurrent neural networks. But actually, if we're a little bit more clever in how we set up the structures of these matrices, we can actually use this representation to represent all commonly used block structured models. So Wiener-Hammerstein, Hammerstein-Wiener, parallel versions of these and so on. So if you're not familiar with these, basically it's variations on a theme of compositions of linear dynamic blocks and nonlinear static blocks. So for our model structure, these linear blocks can be arbitrary stable linear systems, and using the RNN structure, we can have a universal approximator for the nonlinear block phi. So it's a very flexible model class covering many classes that have been used before. Now, before we move on, I'll just say something about incremental stability. So I introduced incremental stability for linear systems, just mainly for convenience. Of course, for nonlinear systems, there are many, many types of stability. So we could have just boundedness of solutions without considering inputs, asymptotic stability or exponential stability with zero inputs, input to state stability, and so on. And in general, these are not equivalent. So we would argue that the two related concepts of incremental stability and contraction are kind of the right ones for system identification. Basically, this is this stability of pairs of solutions from different initial conditions, but with the same inputs to each other. These are, I think, natural because they imply global stability of all possible solutions, not just one that's known in advance, like standard Lyapunov methods. And in system ID, what we're usually trying to do is simulate the model with previously unseen inputs to generate previously unseen solutions. So it's useful that we just automatically get stability of all such solutions. And secondly, they imply that we kind of forget the initial conditions. And in system identification, usually what you're identifying is an input to output map. And so initial conditions are usually unknown anyway. So those are kind of some convenient properties. Okay, so when we've got our RNN model, as we showed above, this kind of linear, nonlinear feedback interconnection, we can represent it in incremental form, like so. Basically, the terms involving biases and inputs disappear. So this is for the linear block. We've got the incremental form. But what about the activation functions? Well, here again, we make use of some quite classical ideas in control, basically that the activation functions satisfy these slope restrictions. Basically, the slope of the function is always between 0 and 1. And we can do a little bit of rearranging to this to put it in a more convenient form. We can rewrite this inequality like so. And then this is an inequality that holds for just a single scalar activation function. But generally, we've got a whole stack of these operating on different signal channels. And if this inequality holds for each of them individually, then we can also take non-negative combinations of these inequalities for the different signals, and that will also hold because we've got a non-negative combination of inequalities is also valid. And we can actually rewrite this in this, this kind of vector inequality where the delta and the delta w's are vectors, and this lambda here represents those non-negative scalings of the individual inequalities. So lambda here is a diagonal matrix which has positive diagonal elements. Okay, so here we've got kind of the final trick that we need. Previously, we kind of combined the model with the multiplier by using an implicit model structure. Here we basically do the same thing to make this inequality jointly convex in the multiplier and also the model term C. We just introduce a new variable C tilde, which is lambda times C. This is, I guess, a standard thing in control theory. So basically now we get an inequality here, which is linear in terms of C tilde and lambda. And since lambda has positive elements and is diagonal from C tilde, we can easily recover C. So now we've got here a linear inequality in terms of our model parameters, which defines the activation functions. Now, then we just do the same sort of thing. We've got the Lyapunov function decrease condition. We've got the same linear block, which equals 0, except now we've got a delta W here. But then we've got a sector condition here on the activation functions. And this we know is non-negative. And since we know this is non-negative, if this whole bit is less than minus epsilon delta squared, then we know this part disappears and this part is non-negative. So that implies that this is less than minus epsilon delta squared for solutions of the model. So basically we get this, this combined condition implies that model solutions will be stable. And furthermore, it's jointly convex in all the multipliers, Lyapunov functions, and model parameters, and can be written as an LMI like so. Okay, so that's basically how we do it. The kind of the novel thing, or the kind of new thing compared to the linear case, is that we've introduced what could be called a behavioral embedding. So basically, we embed the behaviors in the model in a larger set and prove that all models in that larger set are stable. And we can see this is just some examples comparing our model, which we call robust RNN in the green, to several other sets of models, some of which are guaranteed to be stable, some of which aren't. LSTM is kind of the benchmark in RNNs. And basically what we're comparing here is simulation error versus some kind of scaling of the disturbance input, or the scaling of the input to the system. And this is the input that the models were trained on, were fit on. So all the models do pretty well here. But as the size of the input varies, we see that some of the other models get worse, higher simulation error, whereas ours is actually uniformly the best, but it has a much more gradual increase in error as the model, as the inputs vary as well. And here's just some example simulations. You can see that our model, which is in blue, tracks the data quite well and quite smoothly. The other models, in particular, some of them, the LSTM kind of has some periods where it's not tracking very well. If anything, it seems too stable. Whereas the RNN model, which is just the standard form RNN with no constraints, has quite a few of these little kind of kinks in it. So this is this kind of erratic behavior that I mentioned before. Whereas our model is kind of smooth and stable, but not too stable. Okay, so with that, I'll get to the kind of the last main piece of content here. And then there's just a few kind of finishing remarks. So basically we've been able to construct stable sets of both linear and nonlinear models. And we argued that the set of nonlinear models that we used in the RNNs was quite flexible. It contained pretty much every previously known set of stable models of various structures. But there was one limitation, which is that we still used a quadratic incremental Lyapunov function to verify stability. And we know that in general, for nonlinear systems, restricting yourself to quadratic Lyapunov functions can be quite conservative. So an alternative, which I've worked with quite a bit, is something called a contraction metric. And this kind of keeps some of the nice features of quadratic Lyapunov functions, but allows them to be much more flexible by effectively allowing the Lyapunov matrix to vary as a function of state. So here, these deltas should be thought of as small differences. And then M is some Lyapunov matrix that depends on the state. Formally speaking, this defines a Riemannian metric, and delta here are tangent vectors to the state manifold. But you don't really need that formalism for what we're doing. Okay, so the main idea of contraction is basically that local stability everywhere implies global stability of a nonlinear system. And so what we're doing is using this metric, we're analyzing behaviors of these infinitesimals, or basically small differences in solutions. And of course, for a smooth nonlinear system, small differences evolve according to the linearized dynamics. So here, this is the Jacobian of F. And the basic idea is that if this differential dynamics, if basically all linearizations along all possible solutions are stable, then all solutions converge to each other. And so the way you think about this is if you've got a long chain, if every link in the chain gets shorter, then the chain itself must get shorter as well. Okay, and again, motivated by the need for kind of flexibility in our constraint, we use implicit models. And here we're going to be using implicit models of this form. So some nonlinear function E of x plus and u plus is some nonlinear function f of x and u. And for this, we get the differential dynamics like so, where capital E and capital F are the Jacobians of E and F. Okay, so basically what we can do is we can just try using a contraction metric to apply our previous condition. We've got the contraction metric decrease part here, and then this is the condition on the differential dynamics. And this kind of works, but it's a bit inconvenient because if you'll notice, P of x plus and E of x plus require this is the x plus, which is the next state of the system. And this is not arbitrary. This is actually a nonlinear function which depends on E and F. So somehow we'd like to be able to eliminate this from the inequality. And we can actually do that, but not with this metric, with a slightly different metric that actually incorporates some of the model parameters, the model terms, into the metric. So I won't go through the details here, but basically if you take this metric and you just substitute it into here, there's just a bunch of terms that cancel very easily. And you end up with these terms left. And if you'll notice here, there's no x plus appearing anywhere. We've basically canceled all the terms that depend on x plus, and x plus was the part that depended non-linearly on the model E and F. And so this is nice. This can actually be rewritten as a pointwise linear matrix inequality, which for polynomial models can be enforced using sum of squares programming. And again, we notice that basically combining this block and this block, we get that E plus E transpose is strictly positive definite for all X and U. And this is actually a well-known condition for E to be a bijection. So basically this implies that E is a monotone operator in this sense. So basically E of X1 minus E of X2 transpose X1 minus X2 is greater than or equal to some scalar multiple of X1 minus X2 squared. This condition implies that the function E is a bijection, which means that this implicit model is well posed. For every X, U, and U plus, we have a unique solution, X plus. Okay, so that's basically it. Just a toy example to show that this nonlinear metric actually does something. So here we consider just a simple scalar example defined by these equations, E equals 1.1x plus x to the 5, f equals x cubed. If we look at its graph and the slope of its graph everywhere, so the explicit form and its Jacobian, we see that the slope goes well above 1 in some locations, which means that this could never be shown to be incrementally stable with respect to a quadratic Lyapunov function. Basically, there are some regions in state space in which small differences are getting further apart in the terms of the Euclidean distance. But in terms of this non-Euclidean metric, we can actually just substitute this in. We've got our Jacobians here. We substitute this into our condition, and again, a few terms cancel, and we just end up with 1.2 plus x to the 4, which is strictly positive for all x. And so in this scalar example, we can show that we can actually, using this condition, find models which cannot be proven to be stable using a quadratic Lyapunov function. And we've got a bunch of simulation results comparing this structure to the nonlinear ARX structures in the MATLAB system identification toolbox. These are all the various different structures from that toolbox. The key point to look at here is actually the percentages up the top here are the number of times we found an unstable model using these tools. So actually many of the models in the system identification toolbox often found unstable models. And the only one that didn't, this WAV star, it's a wavelet nonlinear ARX model. The star means it did some model structure search. This was the only one that was kind of competitive in terms of simulation error. This should be low compared to our approach, which is over here. This was kind of competitive, but in terms of computation model, it took orders of magnitude longer to find this model than our model. So we think this is kind of proven to be very effective. And again, we can see here, our model is the blue one. This is showing some simulations, and we see it fits well and it's nice and smooth. Whereas using one of the models from the system identification toolbox, it looks nice until you get this kind of sudden jerky behavior. It can be quite erratic in points that you just wouldn't expect. Okay, so I'm mindful of time. I will just kind of very briefly run over some possible extensions and then conclude, and then we can come back to those. I'm willing to stay on afterwards, but I understand people have time limitations. So basically, some extensions we can look at are having Lipschitz constants and incremental L2 gain conditions on the model, as well as just stability. And we can show that we can get kind of a trade-off between robustness and simulation error. We can also have weaker stability constraints that allow us to identify nonlinear models with stable limit cycles, which is something that a linear system can never have. This is actually showing model fit to recordings of a live rat's neuron. And we can also, in fact, use the same ideas for traditional machine learning problems in such as image classification. So there's recently emerged a class of models for machine learning called equilibrium networks, where you basically have a static input-output mapping you're learning, but what you're learning is the equilibrium of a dynamical system. And we can use our stability and robustness constraints to get basically best-in-class performance for these sorts of models and show very good robustness against what are called adversarial attacks in image classification. So I'm happy to come back to some of those things, but I'll conclude now, given that I'm just about out of time. Basically, the conclusion is that stability or stability-like constraints can be very useful in nonlinear and linear system identification and also other problems. The main technique that we have developed and applied in a number of ways is to combine the flexibility of implicit models and kind of S procedure-like or positive Stellensatz like arguments to construct convex sets of stable models. But I will say that basically, I think we're just scratching the surface. There's lots of scope for flexibility and generalization to different problems and different model sets and so on. So I'll finish there. Thank you.
Thanks, Ian. We might have time for one very quick question. Otherwise, I ask people just to email Ian directly. Is there any question? Just a quick one. Okay, let's just wrap it up. Thanks, as the time is up, so other people can go to other things. But yeah, maybe if you can hang around for 5 minutes, if anyone wants to ask a question, that would be great. Thanks.
Thanks.